Hello, good evening all. I am Saurabh and I welcome all of you to this live session for the NPTEL course Applied Thermodynamics. In today's session, we will solve some problems related to gas turbine engines. Okay, so let us begin our discussion. Okay, so this is question number 1. It says that in a Breton cycle, the specific work output is maximum at minimum value of pressure ratio. So we have to tell that whether this statement is true or false. So, you know, Breton cycle, if we make the PV diagram, then we know that there is isentropic compression, then heat addition at constant pressure, then isentropic expansion in turbine. Okay, so there are two isentropic processes and two isobaric processes. This is our ideal Breton cycle. Okay, so in Breton cycle, if you try to write the specific work output, then this you can write it as Cp T3 minus T4. This is turbine work, but there is also some work consumed by compressor, right? So you'll have to subtract that work. So the compressor work is Cp T2 minus T1. We can also make the TS diagram. So 1 to 2, there is isentropic compression. This is TS diagram. Then 2 to 3 is isobaric heat addition. Then expansion in turbine. Okay, isentropic expansion. And then there is heat rejection. Okay, so this part is compressor work. Okay, so the net work output that you are getting, that is this first term minus this second term. Okay, that is your specific work output. Okay, so if you try to write this specific work in non-dimensional form, then you can divide the whole thing by Cp T1. Okay, so T1 is the initial temperature. Okay, so if we divide both sides by this term, so we'll get T3 by T1 minus T4 by T1 minus T2 by T1 minus 1. Okay, and there is something called pressure ratio. So pressure ratio is nothing but the ratio of final pressure to the initial pressure at compressor. Okay, so at the outlet of compressor you have P2 and at the inlet you have P1. So this is our pressure ratio, R, let us say. Okay, and pressure at point 2 is equal to pressure at point 3, right? Because heat addition takes place at constant pressure, and P1 is equal to P4. Okay, so we can write this non-dimensional specific work in terms of R. Okay, so this can be written as T3 by T1 1 minus R to the power gamma minus 1 by gamma. So gamma is ratio of specific heats, right? Because 2 to 3 and sorry 1 to 2 and 3 to 4, these are isentropic processes, so you can use adiabatic relation. Okay, P1 V1 to the power gamma is equal to P2 V to the power gamma. Okay, so minus R to the power gamma minus 1 by gamma minus 1. So this is your specific work. Okay, so this is nothing, just we are writing this specific work in terms of pressure ratio. Okay, using the adiabatic relation. Okay, so I hope that terms, the definitions are clear, so we can proceed to solve this question. Now it is saying that a specific work output is maximum at minimum value of pressure ratio. So we have to tell that this specific work, how it is related to pressure ratio. If you increase the pressure ratio, then what will be its effect on a specific work output. Okay, so if we plot this specific work output against pressure ratio, then you will get, okay, so these types of plot. Okay, this is our specific work, and x-axis we can keep pressure ratio. So this will look something like this. Okay, so we can see that specific work increases with increase in pressure ratio. So what are these different line? uh, these are basically these temperature ratios. Okay, so T3 by T1, if we write it as small t, so this is, let us say, t is equal to 1, this is t is equal to 2, let us say it is t is equal to 2, it is 3, and so on. Okay, you can use any graphing calculator. Okay, and for different t and for constant gamma value, you can find this plot. Okay, so from this plot you can easily say that on increasing pressure ratio, the specific work output also increases. Okay, so it is saying that specific work output is maximum at minimum value of pressure ratio. So this is false, right? Because at minimum value of pressure ratio, the specific work will also be minimum. Okay, so this statement is not correct. This is false. Okay, so I hope that these definitions and little bit about this formula, how do we calculate the specific work output, how it is dependent on pressure ratio, these things are clear. Okay, so this is very important because many upcoming questions will be related to these concepts. Okay, so if it is clear, then we can move to question number 2. Question number 2 says, in a gas turbine, intercooler is placed in between high pressure compressor and turbine. So before solving this question, we should understand what does different terms mean. Okay. Intercooler. What is an intercooler? What is a high pressure compressor? So as we discussed in the previous question, that first of all, the air is compressed in a compressor. Okay. So air is compressed in a compressor. I am making the TS diagram from 1 to 2. It is compression. Okay. Then constant pressure heat addition. Then 3 to 4, it is expansion in turbine. Okay. So turbine produces the work, but compressor consume the work. Okay. So if you are compressing the air, so basically you are putting some work, you are giving some, providing some work to the compressor. Okay. And we know that compressor work is minimum if the compression process takes place at constant temperature. Okay. Isothermal compression takes the minimum work. Okay. And also you can see that I will make this graph again so it will be more clear. You can see that distance between this constant pressure lines is increasing as we go to the right. Okay. So this gap and this gap, if you compare, then you can see it is increasing. Okay. So if you want to reduce the compression work, then you should try to compress the gas, compress the air at low temperature. Okay. So when you compress the air, it becomes hot, and to reduce the compression work, you should cool that gas. Okay. So instead of compressing the air in single stage, you what we do is we compress it in more than one stages. Okay. Maybe 2 stages or 3 stages. Okay. So first we compress it in a compressor that we can call as low pressure compressor. Okay. So then you can pass this gas to a heat exchanger. Okay. Basically intercooler. Okay. Then again you can compress this gas in another compressor. Okay. So the first one is our low pressure compressor, and second one is high pressure compressor. Okay. Then this compressed air will be passed through combustion chamber. Okay. Where the fuel will be burnt. Okay. Then you will have turbine. Okay. So intercooler is basically placed between a low pressure compressor and high pressure compressor. Okay. And the purpose of intercooler is to reduce the compressor work. Okay. So now you can easily answer this question, that intercooler is not placed between high pressure compressor and turbine. Between high pressure compressor and turbine, there is combustion chamber, not the intercooler. Okay. So this statement is not correct. So this is false. Okay. Okay. I hope this is clear, and we can move to the next question. Question number 3. It says that at high subsonic speeds, so subsonic means the speed is less than the speed of sound, okay? And high subsonic speed means the speed is high, but it is still less than the speed of sound, okay? So speed of sound is approximately 330 or 340 meter per second. So the high subsonic speed means something around 280 or 300, like that. Okay, so at high subsonic speed, a propulsive jet of smaller mass flow but higher velocity is achieved by a turbofan or bypass engine. So you can easily answer this question, and this statement is true. Okay, so we will see a diagram, so it will become more clear. Okay, so basically we are talking about a turbofan or bypass engine. So what it is, we can see this in this diagram. Okay, so in a turbojet, what we have incoming air. Okay, so this air is passed through this compressor, right? Then this compressed air goes into combustion chamber. Okay, combustion chamber, then turbine. Okay, it expands in turbine, and then it goes into nozzle. Okay, so this is our turbojet engine. Okay, but in a turbofan engine, what we have, this turbojet engine, this is common in both. Okay, these I mean this part is similar in both, but in turbofan we have some extra components. So what are those extra components? There is fan. You can see here at the inlet there is some fan. Okay, so there is this fan, and there is this small duct. Okay, and the inner core is similar in both engines. Okay, so that is like common. Okay, so what fan do is it sucks the air in and sends some part, the little air, into this duct. Okay, so propulsive jet of smaller flow. Okay, we are sending a small amount, not the, most of the part is going through this inner core. Okay, that is going into the combustion chamber, but some part of that air goes through that duct. Okay, so that duct provides high exit velocity at the end. Okay, so here you have very high velocities. So because of this high velocity you get some extra thrust. Okay, so in the second part also you can see in the second figure it is more clear that in the inner core, that is our primary section. Okay, that is primary stream, because most of the air is going inside the primary stream. Okay, the maximum air. Okay, and some part of that air is going into this fan stream. Okay, so in the fan stream the mass flow rate is low, and in this primary stream it has more mass flow rate. Okay, so this is our turbofan. The inner core is common in both turbojet and turbofan. Turbofan has this extra part. Okay, this fan and this duct. So this statement is true. Okay, a propulsive jet of smaller mass flow rate but higher velocity is achieved by turbofan. So I hope this is clear, and we can move to question number 4. Question number 4 says the enthalpy drop in moving blades and fixed blades of a steam turbine. Okay, so please be careful. So we are discussing about gas turbines, but here we have steam turbine. in this question anyways. But we have discussed the steam turbines, so we can easily answer this question. So it is saying that enthalpy drop in moving blade and fixed blade of a steam turbine is 20 kilojoule per kg and 34 kilojoule per kg respectively. And we have to tell the degree of reaction. Okay. So in steam turbines, you have studied the degree of reaction. How do we define degree of reaction? Degree of reaction is defined as enthalpy drop in moving blades divided by total enthalpy drop. Okay. So we know that there are some fixed blade, stator blade, and there are some moving blades. Okay. So some enthalpy drop take place in moving blade and some enthalpy drop take place in static blades. Okay. So the ratio of enthalpy drop in moving blades to the total entropy drop, total enthalpy drop, that ratio we call as degree of reaction. Okay. So enthalpy drop in moving blade is given to be 20 kilojoule per kg, and total enthalpy drop will be summation of these two components. Okay. 20 plus 34 kilojoule per kg. Okay. So you can calculate this value. Okay. So it is coming around 0.37. So please calculate this value and check that you are getting the same answer. Okay. So if it is any mistake, just let me know. Okay. So option B, this is the correct option. Okay. So this was question from steam turbine, but I hope that you was able to solve this question. Just a definition based question, definition of degree of reaction. Okay. So if it is clear, then we will move forward to question number 5. Okay. Question number 5 says that the optimum pressure ratio for maximum specific output for ideal gas turbine power plant operating at initial temperature of 300 Kelvin and maximum temperature of 1000 Kelvin is what? Okay. So we have to calculate the optimum pressure ratio. And it is saying that we can take the specific heat ratio for air to be 1.4. Okay. So gamma is given to be 1.4. Okay. So in some previous question, we have discussed the expression, the formula for specific output, right? So specific output in non-dimensional form, that was this formula. R to the power minus 1 by gamma minus R the power gamma. Okay. So this is nothing, just this is, total work output, net work output divided by CPT1, and the net work output is turbine work output minus compressor work input. Okay. So this is your specific work output. Okay. And the maximum specific work output, if you want to find the maximum specific work output, then you will have to differentiate this expression with respect to R and make that differentiation equal to 0, right? Because for maxima or minima, that's what we do, right? We differentiate the expression with respect to our variable, and we set that difference is equal to 0. And here the variable is r, and instead of r we can take this r to the power gamma minus 1 by gamma. Okay, so let us replace this r to the power gamma minus 1 by gamma is equal to x. Okay, so you will have the specific output is equal to, and let us write t3 by t1 is equal to small t. Okay, so you'll have a small t 1 minus 1 by x minus x minus 1. Okay, so for maximum specific output we can differentiate this thing d by dx of w by cpt1, and we will make this thing is equal to 0. Now you can easily differentiate this thing. The differentiation question, mathematics question. T1 minus 1 by x square, and this will become plus minus 1 is equal to 0. So you have 1 plus x square is equal to 1 by t, right? I have made one mistake. This 1 will not be there. Okay, so I will write it again, because differentiation of 1 is 0. Okay, so it will be key, it will be t plus 1 by x square minus 1 is equal to 0. Okay, now it is correct. Okay, so we have 1 by x square is equal to 1 by t, or you can write x optimum value. Okay, so x was nothing but r to the power gamma minus 1 by gamma optimum is equal to under root t, right? So this is our relation for optimum pressure ratio. Okay, and t is defined as T3 by T1. Okay, so T3 is the temperature at outlet of combustion chamber, and T1 is the inlet temperature. Okay, so in this question the maximum temperature, that maximum temperature is given to be 1000 Kelvin, so that is T3, and inlet temperature or the minimum temperature is 300 Kelvin. Okay, so if you find this value, okay, so this is r, this is r to the power gamma minus 1 by gamma is equal to under root of 1000 divided by 300, and we have to find optimum pressure ratio, right? We have to find r, so r will be equal to 1000 by 300 to the power gamma into gamma minus 1, and gamma is given to be 1.4. So you can just substitute the values and you will get like this. Okay, so if you calculate, then you find optimum value of pressure ratio. I have calculated this value and it is coming 8.22. So I request you to please check this calculation, and if there is any mistake, please let me know. Okay, so this is like a standard formula, but I have again derived so that in any case if you forget this formula, you should be able to derive how we are getting this expression. Okay, you can directly use this expression, but it is always better to know from where we are getting this. Okay, so optimum value of pressure ratio in this question we are getting to be 8.22. So let us check all these options: 4.2, 8.2, 12.2, or 14.2. So option B is the closest option, right? So part B should be the correct option, 8.2. Okay, so I hope this is clear. Once again, I can repeat that a specific output depends on pressure ratio, and for to calculate the maximum specific output, you can differentiate the expression for a specific output with respect to your pressure ratio, or you can differentiate the expression for a specific output with respect to r to the power gamma minus 1 by gamma, so that it will become easy for differentiation, and you can set that differentiation equal to 0, so you'll get the optimum value for pressure ratio. Okay, I hope this is clear, and we can move to the question number 6. Next question. Okay, question number 6. The specific power output of a turbine in a Breton cycle is at 36.5 kilojoule per kg. Okay, so this is our specific power output. Okay, and specific power output will be given by the same expression, right? Cp T4, sorry, T3 minus T4. This is turbine output. Okay, so if you want to find the net output, then you will have to subtract the compressor work. Okay, but here it is given to be output of a turbine. Okay, so this is given to be 336.5 kilojoule per kg. Okay, the exhaust gases leave the turbine at 700 Kelvin. So T4 is given to be 700 Kelvin. Cp is given to be 1 kilojoule per kg Kelvin, and gamma is given to be 1.4. The turbine pressure ratio is, so again we have to find the pressure ratio. I will quickly make the TS diagram. So 1 to 2 it is isentropic compression, 2 to 3 it is isobaric heat addition, 3 to 4 is turbine expansion in turbine. Okay, so we have to find turbine, sorry, what happened? We have to find turbine pressure ratio. So turbine pressure ratio is P4 by, sorry, P3 by P4, right? And if you assume this thing to be, again, to be isentropic, then you can use the adiabatic relation. Okay, so using adiabatic relation, you can write P3 by P4 is equal to T3 by T4 to the power gamma minus 1. Okay, right? T3 by T4. Okay, T4 we have, and from this first expression we can find T3, right? So T3 will be equal to 336.5 divided by Cp. Cp is just 1 plus T4. T4 is 700 Kelvin. Okay, so T3, this will come out to be 1036.5 Kelvin. So please do this calculation and check if I am doing correct. So just substitute the values. 1036.5 divided by T4 is 700 Kelvin to the power gamma is 1.4 divided by 0.4. And if you find this value, try to calculate this value, this will come out to be 3.95. Okay, so this is P3 by P4. This is our turbine pressure ratio, right? This is okay. So I hope this is clear, and we can move to the next question. Question number 7. This is also the numerical question. It says that gas power plant operating on Brayton cycle at minimum pressure, minimum temperature as 40 degrees Celsius and 800 degrees Celsius respectively. The optimum specific work we have to find, and we can take the heat at constant pressure as 1.005. So Cp is given, right? Okay, so we have done the similar question, only just numerical values are different. Okay, okay, so this is exactly same as question number 5, just numerical values are different. Okay, so again, I'm not, we will not derive the formula, we will just use the formula. Okay, so here is the formula. We will use this expression. Okay, r to the power gamma minus 1 by gamma, this is optimum pressure ratio, is equal to under root T. T is T3 by T1. Okay, so yes, this is the expression. Okay, so T3 is 800 degrees Celsius, but we need to change this value to into Kelvin. Divide by 40 plus 273, and we need to take the square root. Okay, so if you calculate this value, you can calculate this value. Okay, but in this question, what is asked is, okay, we don't need to find this our optimum. We have to find optimum specific work, right? We have to find W max, right? So we will directly write the formula for W max. So W max is T 1 minus 1 by root T minus root T minus 1. Okay. So T is T3 by T1, that is 800 plus 273 divided by 40 plus 273. And if you calculate this value, this will come out to be 3.43. Again, just please check this calculation. Okay, so this is optimum value. Okay, and if you just substitute the values for T, you will get under root 3.43 minus root of 3.43 minus 1. Okay, and if you calculate this value, this comes out to be 0.725. Okay, this is W by CPT1, and we have to find W max. Okay, so W max will be equal to 0.725 into Cp into T1. So Cp is given 1.005 and T1 is given 40 plus 273. Okay, so 0.27725 into 1.005 into 40 plus 273. I am writing the everything is in SI units, so this will be in kilojoule per kg. Okay, so if you calculate this value, this will come out to be, I am writing the final value, this is coming out to be 228, approximately 228 kilojoule per kg. Please check this calculation. If you are getting something different, just let me know. Okay, so this is our answer. Okay, the answer is approximately 228. Okay, so again, this was a similar question, similar to question number 5 or 6. 5, yes. Okay, so I hope this was a easy question to solve. So if there is no doubt, then we will move forward. We have question number 8. Question number 8 says, in a single stage open cycle gas turbine, the mass flow through the turbine is higher than the mass flow through compressor. So what does it mean? First, we have a compressor. Okay, first we have a compressor. Then we have compressed air goes into combustion chamber. In combustion chamber, some fuel is injected, right? And that fuel burns and the exhaust gases passes through the turbine. Okay, so it is saying that mass flow rate at the turbine outlet, mass flow rate at exit of turbine is greater than the mass flow rate through the compressor. Okay, so mass flow rate at compressor, let us say it is MI, mass flow rate inlet. So it is saying that ME is greater than MI. So yes, it is correct. Why? From where this extra mass is coming? This is coming from the combustion chamber. In the combustion chamber, you are adding some fuel, right? Correct. So that extra mass appears as increased mass flow rate at the outlet of the turbine. Okay. So let us check all these options. Option A says that this is because the specific volume of air increases by the use of intercooler. There is it has nothing to do with the intercooler. Option B says the temperature of air increases in the reheater. Again, it is single stage open gas turbine, right? So single stage means we are not reheating. It is just single stage. Part C says the combustion of fuel takes place in the combustion chamber. Yes. And last part says the specific heats at constant pressure for incoming air and exhaust gases. So even if the specific heats are changing, it will not affect the mass flow rate, right? The mass flow rate is increased at the exit as compared to inlet because we are adding some fuel in the combustion chamber. So part C should be the correct option, right? The combustion of fuel takes place in the combustion chamber. Okay, so this is because of fuel injection in the combustion chamber. Okay, so I hope this to question number 8 everything is clear and we can move to the next question. Question number 9. Question number 9 says that a gas turbine power plant operating on Breton cycle has maximum and minimum temperature as 800 degrees Celsius and 40 degrees Celsius. We have to find the optimum specific work. So this is the repeated question. So we have already solved this question, right? Somewhere. Yes, it is same as question number 7. So the specific work. Okay, we had calculated the specific work. And in question number 9 also we have to calculate the optimum specific work. So the answer was, sorry, answer was 228 degrees. Sorry, 228 kilojoule per kg. Okay, so here option C should be correct option, right? This is same as question number 7. Okay, so we will move to the next question. Question number 10. Question number 10 says A heat exchanger can be used only if there is sufficiently large temperature difference between the gases leaving the turbine and air leaving the compressor. Otherwise, it will incur additional capital cost and maintenance requirement. So we know that why we are first of all we should understand that why we are using heat exchanger. We are using the heat exchanger to utilize the heat content in the exhaust gases, right? Because the exhaust gases which are coming out from the turbine, those gases you are throwing into the environment, okay? And those exhaust gases had a large amount of heat, right? So if somehow you can utilize that heat, then your efficiency will, improve, right? So what we do, we pass those hot gases, those hot exhaust gases through a heat exchanger. And with the help of that heat exchanger, we increase the temperature of the air coming out from the compressor. Okay, the air which is coming out from the compressor and that is going to the combustion chamber. So that air, instead of directly sending that air to the combustion chamber, we can send that air to the heat exchanger, so that temperature will be increased, right? So in that manner we are utilizing the waste heat. Okay, so now let us see uh, if we can solve this question. The heat exchanger can be used only if there is sufficiently large temperature difference. Yes, there should be temperature difference. Only then there will be heat transfer from the exhaust gases to the air coming out from the compressor. And it is saying that there should be sufficiently large temperature difference between the gases leaving the turbine and air leaving the compressor. Yes, if there is not sufficiently large temperature difference, then there will be very less heat transfer, right? Because heat transfer depends on the temperature difference. And if there is very less heat transfer, then there is no point of putting this extra infrastructure, okay, extra equipment, extra this heat exchanger. Okay, so if there is not sufficiently temperature there is if there is not sufficiently large temperature difference, then it will incur additional capital cost and maintenance requirement. So yes, it is correct, right? So we cannot blindly put you know extra equipments. Okay, it is not like we will make the system complicated and it will always be beneficial. It is not like that. Okay, whenever you are putting some additional component, it can increase the efficiency a little bit. But if the uh, money that you saved because of increased efficiency, if that money is not significantly higher than the additional capital cost and the maintenance charges, then there is no point, right? So the option, so this statement is true, right? So heat exchanger should be used only if there is sufficiently large temperature difference, so that we do not incur additional capital cost and maintenance requirement. Okay, and also uh, this will make the system bulkier, right? Not only capital cost and maintenance, this will also make the system heavy, right? So I hope everything is clear up to this question number 10. So if there is no doubt, then we will move to question number uh, 11. Next question. Question number 11 says that which of the following parameters are of importance with respect to the performance of an ideal gas power cycle, ideal gas power plant. Okay, so option A says the work output, option B says efficiency, option C says specific fuel consumption, and D says none of these. So this is very easy. All of these parameters are important, right? We want higher work output, right? We want more efficiency. We want less fuel consumption. So all of these parameters are important. So which of the parameters are important with respect to performance of an ideal gas power plant? So work output, we want more work output. Similarly, more efficiency and less, we want lesser specific fuel consumption. So all of these, are important parameters. So option A, option B, and C, all these three options are correct. Okay. So I hope that this is clear, and we can move to the next question. Question number 12. It says that multi-stage compression with intercooling and multi-stage expansion with reheating in a gas power plant is intended for improving. Okay, intercooling we have already discussed, right? So intercooling, it reduces the compression work. Okay, and we also discussed this concept with the help of TS diagram. We discussed that instead of compressing the whole air in one stage, we can compress this thing in more than one stage. Similarly, okay, so you can see that towards left, the gap between these constant pressure lines is less, and as you move towards right, the gap becomes wider. Okay, so if you want to reduce the compression work, you should try to move towards left, right? So that compression work will be less. And if you reheat, then you move towards, right. So again, the gap increases. So you are reducing the compression work and you are trying to increase the turbine work. Okay. But if you talk about intercooling, then yes, compression work is reduced, but the total heat input increases, right? So what I mean is that if you would have compressed from 1 to 2 dash, let us say directly, then the heat addition will take place from would have been taken place from 2 to 2 dash to 5, right? Without intercooling. Without intercooling, the heat input will be from 2 dash to 5, right? But with intercooling, the heat addition will be from 4 to 5, right? So after intercooling, you have to put more heat input. Okay. So yes, you are reducing the compression work, but you are increasing the heat input. Okay. So in most of the cases, the efficiency will drop. Okay, because of the increased heat input. Okay. So let us see all these options one by one. uh, Option A says to improve the cycle efficiency, to increase the power output. Option C says both power output and efficiency, and power D says none of these power output. Okay, so what will happen if you reduce the reduce the compression work and increase the turbine work? What will happen? If you increase the turbine work and reduce the compression work, the net work output will increase, right? Because the total net work output is turbine work output minus compressor work input. Okay, so basically you are increasing the turbine work output and you are increasing the turbine work output and you are reducing the compression work. So basically overall work output will increase. Okay, but in most of the cases the efficiency will drop. Okay, so only part B should be the correct option. Okay, please note that the efficiency can be dropped. Okay, it can be reduced. So power output will of course increase, but efficiency can be decreased. Okay, so part B is the correct option. Okay, so I hope that this intercooling and reheat thing is clear, and this point that power output will be increased but the efficiency can be decreased, that is also clear. And to compensate this decrease in efficiency, we use the heat exchanger, right? Because the exhaust gas, as we discussed earlier, that exhaust gases have uh, a large amount of heat. So using the heat exchanger you can utilize that heat. Okay, so that heat exchanger will compensate for the efficiency. Okay, so basically the efficiency will be increased if you use the heat exchanger. Okay, I hope this is clear, and we can move to the question 13. Question 13 says intercooling in gas turbine. Okay, so again the same question. The intercooling in gas turbine decreases the net output but increases thermal efficiency. Part B says increases net output but decreases thermal efficiency. Part C says decreases both net output and thermal efficiency. And last part says that it increases both net output and thermal efficiency. We discussed that it increases the net output, but it in the most of the cases it decreases the thermal efficiency. Okay, so part B should be the correct option. Okay, because the thermal efficiency is the net work output and heat input. So intercooler increases this network output, but it also increases Qin. Okay, so in most of the cases, this efficiency decreases, even though the W is increasing. Okay, so part B should be the correct option. I hope this is clear. So now we have question number 14. Okay, this is numerical question. It says that air enters a gas turbine with two stages of compression, two stages of expansion. Okay, at 100 kilopascal and 17 degrees Celsius. This system uses a regenerator as well as reheating and intercooling. Wow. The pressure Okay, so this is regenerator is nothing but the heat exchanger. Okay, so it has heat exchanger as well as reheating as well as intercooling. The pressure ratio across each compressor is 4. Okay, and 300 kilojoule per kg of heat is added to the air in each combustion chamber. Okay, fine. And the regenerator operates perfectly while increasing the temperature of cold air by 20 degrees Celsius. Okay, we have to find the system's thermal efficiency, assuming the isentropic operation for all compressor and turbine stages, and use the constant specific heats at room temperature. Okay, nice. So there are a lot of steps. There is regenerator, there is reheating, there is intercooler. Okay, so we should, I mean, read the question again and check this figure for better understanding. Okay, so first let us start from this point A. The air is going to the first compressor, the low pressure compressor. Okay, then after low pressure compressor at point 2, it is going into intercooler. Okay, so this will become little cold. Okay, then after intercooler it is passing through a high pressure compressor. Okay, so after high pressure compressor it is going to the heat exchanger, right? So after heat exchanger at this point 5, after heat exchanger it is going into, so this is our heat exchanger. In question it is writing as, it is given as a regenerator. So regenerator is nothing but heat exchanger. Okay, heat exchanger or regenerator, both are same. Then after regenerator it is going into combustion chamber. Okay, then it goes into turbine. Okay, the high pressure turbine. Then it is reheated. Okay, in another combustion chamber. Okay, so this is another combustion chamber. Then again it is passed through another turbine. Okay, then after turbine it is going to the heat exchanger or the regenerator. Okay, this is the how the whole this is how whole system is working. Okay, so in question few values are given. At kilopascal and 17 degrees Celsius is the value at inlet. So one more thing you should note here is that gas enters a gas turbine. So this does not mean that gas is going into this turbine at 100 kilopascal and 17 degrees Celsius. So it basically means that at the inlet of this whole gas power plant, the air was at 100 kilopascal and 17 degrees Celsius. Okay, this does not mean that 100 kilopascal and 17 degrees Celsius are the turbine inlet condition. It is not like that. Okay, and as we discussed, that regenerator is nothing but a heat exchanger. Okay, before proceeding we should make the TS diagram. Okay, First of all, there was compression from 1 to 2. Then there was a intercooler 2 to 3. Then another second stage compression 3 to 4. Okay. Then 4 to 5 was our heat exchanger. Then 5 to 6 was the first combustion chamber. Then 6 to 7 was first turbine. Then 7 to 8 was another combustion chamber. 8 to 9 was again the second turbine. Then 9 to 10, this part was going, this was cooling of exhaust gases in the regenerator or heat exchanger. Okay, so this is our TS diagram. Okay, so these points are marked in this diagram. So you can see that which component is undergoing under which type of process. So we will assume that all the processes are ideal. Okay, and the air is ideal gas, and its properties we will take to be constant, and we will take the values at room temperature. Okay, so let us begin. Properties of air, first of all, we will require them a lot, so we can write it as Cp is equal to 1.005 kilojoule per kg Kelvin, and K or gamma, whatever, is 1.4. Okay, and one more point, that since the inlet conditions at inlet condition of both the compressor is same, and the compression ratio is same, right? The efficiency and every other thing is same. So we can write as T2 is equal to T4. Okay, and T1 is equal to T3. This is the inlet condition. And similarly for turbine, you can write T7 is equal to T9, and T6 is equal to T8. Okay. So since from 1 to 2, the process is isentropic compression, we can use the adiabatic relation. Okay. So T2 can be found from adiabatic relation, that will be equal to T1 into RP. RP is basically pressure ratio to the power K minus 1 divided by K. So if you substitute the values, you will get what was the inlet temperature. This was 17 degrees Celsius, right? So T1 is equal to 17 degrees Celsius or 290 Kelvin. Okay, 290 Kelvin, and this RP, pressure ratio, was 4. Okay, across each compressor. RP is equal to 4. So can write 4 to the power 1.4 minus 1 divided by 1.4. And if you calculate this value, I have already, these final values. So I will copy the values. Okay. You please check all these values after doing your own calculation and let me know if there is any mistake. So T2 is coming out to be 430.9 Kelvin. Okay. So T4, since this is equal to T2, that will also be equal to 430.9 Kelvin. And it is given that regenerator increases the temperature by 20 degrees Celsius. Okay, so the heat exchanger increases the temperature by 20 degrees Celsius. So T5 will be equal to T4 plus 20 degrees Celsius, right? So 430.9 Kelvin plus 20. So this will be temperature at 0.5 at the exit of regenerator. Okay, so this will come out to be 450.9 Kelvin. Okay, now from 5 to 6 there is heat addition in combustion chamber. Okay, so heat addition in combustion chamber. Okay, this was generator. Now there is heat addition in combustion chamber. Okay, so Q in is equal to Cp T6 minus T5. And heat addition, it is given that heat addition in each combustion chamber is 300 kilojoule per kg. Okay, so Q in each stage is 300 kilojoule per kg per stage. Okay, in each stage. Okay, so we have 300 is equal to, I'm not writing the unit because everything is in SI units. Okay, just keep that in mind. Okay, is equal to Cp is 1.005, T6 minus T5 is 450.9. Okay, so from this expression you can find the T6. Okay, if you calculate the T6, it will come out to be 749.4 Kelvin. Okay, so again I am copying the value which I have. Okay, you please do your own calculation and check that if everything is correct or not. Okay, so this is after the first combustion chamber. Then after first combustion chamber you have the first turbine, right? Then you have, this is combustion chamber 1, or in the first combustion chamber. Then you have first turbine. So since we are assuming that all the processes are reversible, so the expansion in turbine should be isentropic. Okay, and we can use the adiabatic relation. So temperature at the outlet of the first turbine can be written as T7 is equal to T6 into 1 by Rp to the power k minus 1 by k. Okay, this is just the adiabatic relation. And if you just substitute the values, you will get T6 is 749.4 Kelvin and 1 by Rp is 4, right? 1.4 minus 1 by 1.4. Okay. If you just calculate this value, I'm again copying. Okay. So if you calculate this value, this will come out to be T7 is equal to 504.3 Kelvin. So again, I encourage you to please do this calculation by yourself and check if everything is fine. Okay. So this was the first turbine. Now after first turbine, you have the second combustion chamber. In second combustion chamber also there will be heat addition of 300 kilojoule per kg. Okay. So heat addition again 300 kilojoule per kg, right? So this heat addition will increase the temperature, and temperature at the outlet of this second combustion chamber will be equal to T8 is equal to T7 plus Qn divided by specific heat. Okay. So T7 you already have this value 504.3 plus Qn is 300 kilojoule per kg divided by the specific heat. Specific heat is 1.005, right? Okay. So you have T8 is equal to T8 is equal to 802.8 Kelvin. So gradually we are getting the values from values at all the points. Now after second combustion chamber, you have second turbine or the low pressure turbine. The low pressure turbine. Okay. In the second turbine, the process will be isentropic expansion. Okay. So you can use the okay. So from the adiabatic lesson, you have T9 is equal to T8 into 1 by Rp to the power k minus 1 by k. Okay, if you just substitute the values, you will get 802.8 is the T8 into 1 by 4 to the power 1.4 minus 1 divided by 1.4. Okay, so if you calculate this value, then you will get T9, and T9 here it is given, it is coming out to be 540.2 Kelvin. Okay. Okay. So this was our second turbine. So after the second turbine, this will go into regenerator or heat exchanger. Okay. So in heat exchanger, there was change in temperature by 20 degrees Celsius. So at the end of at the outlet of regenerator, the temperature of exhaust gases will be dropped by 20 degrees Celsius. Okay. So T10 will be equal to T9 minus 20 degrees Celsius. Okay. So you will have 520.2 Kelvin is equal to T10. Okay. So now we have temperature values at all the points. Okay. at the inlet and exit all the components. Okay. Now we can find whatever is asked in the question. So what is asked? We have to find the system's thermal efficiency. Okay. Thermal efficiency. Thermal efficiency is given by work output by heat input. Okay. Or in other words, you can write from the first law of thermodynamics, the work output will be equal to heat input minus heat out divided by heat input, or neta is equal to thermal efficiency is equal to Q out divided by Q in. Okay. So where is the Q out? We have to find this quantity. This is, first of all, some heat is rejected into environment. If it is a open cycle, then you will throw the gases coming out from the regenerator into the environment. So one such heat rejection is at after point 10. Okay. And 2 to 3. Okay, in the intercooler. Okay. So Q out, if this was an open cycle, then the gases will be thrown into environment. Otherwise, somehow you will have to begin the system back to the original condition. Okay. So one is 10 to 1, and another part is it has two components. Q out has two components, and another one is 2 to 3. So 2 to 3 is basically intercooler. Okay. So Q out, if you write, then you will get Cp T10 minus T1 plus Cp T2 minus T3. This is intercooler. And if you substitute the values, you will get Q out is equal to 1.005. I'm not writing the units. 90 plus 430.9 minus 290 degree. Okay. So this value is coming out to be 373.0 kilojoule per Kelvin. Sorry, kilojoule per kg. This is Q out. So now you have Q out, you have Q in. Q in is taking place in two parts. Okay. Q in is taking place twice. Okay. Because there are two combustion chambers. So Q in is equal to 300 plus 300 kilojoule per kg. Okay. So now you have Q in, you have Q out, you can calculate the efficiency. And there was one more way we could have find out the net work output. So for calculating the net work output, you will have to uh, add the work output from both turbines, then subtract the work input to the both compressors. Okay. So that would have been little more involved, but that was also one way. Okay. Now you can find the efficiency, thermal efficiency, that is equal to 1 minus Q out by Q in. Just substitute the values, you will get 1 minus 373 divided by 600 particle. Okay. So it is coming to be 0.378 or 37.8%. Okay. So this is our answer. So when you make the TS diagram, then it becomes easy because it gives a glimpse that what values we have, what values we need to find, and what are the processes, what can be the formulas that can be used to find the unknown values. Okay, so this was question number 14. Okay, so I hope that everything is clear. So this was the last question. Okay, so we have seen the specific work output, then how to write this specific work output in terms of pressure ratio, how this specific work output depends on pressure ratio, then how to find the maximum specific work output, then why do you use intercooler, what is the effect of intercooler, then the difference between turbofan and turbojet. Then we discussed one question related to steam turbines degree of reaction. The degree of reaction is enthalpy drop in moving blade divided by total enthalpy drop. We saw that how to find the maximum specific output by differentiation, by making the differentiation equal to 0. Okay, then we solved some questions related to you know specific related to optimum pressure ratio. Okay, we discussed one important uh, thing, that intercooler and reheat, these arrangements increases the total work output, but they can you know result into result in drop in efficiency. Okay, and we also discussed that heat exchanger and any additional component should be used only when it justifies its additional capital cost and maintenance requirements. Okay, we discussed that work output efficiency, specific fuel consumptions are very important parameters. Okay, then we solved a question, numerical question, that was related to a gas power plant which has a regenerator. Regenerator is basically heat exchanger as well as reheating and intercooling. Okay, so I hope that these questions will be helpful for you in solving your assignment problems, and I hope that it might have cleared some of the doubts that you might have. Okay, okay, so thank you. We will stop here and we will meet in the next session. Okay, till then, bye, take care.